All right, next in our unit, we're going to be graphing logarithms. So if you look at your notes, the first thing we're going to talk about is how we've been converting from exponential to log form in the past during this unit. And we know that those two forms are related, exponential and log, because we go back and forth between them. What you might not have realized is that they are actually inverses of each other. So for instance, if I write the equation y equals base to the exponent of x, and I want to find the inverse of that, I just need to trade my x and my y. So I would say x equals b to the y. And if we weren't picky, we could say, all right, the green part, that's the inverse, and I'm completely done with the problem. But we know that usually you need to have the y all alone in the problem. And the only way to get y all alone in this problem is to rewrite this as a logarithm. So when I write this, I'm going to have log with a base of b, and then I have to do the Tootsie Roll, and this one's kind of set up weird, where you have to do the Tootsie Roll backwards, but we have to go around. So log base b of x equals y. And this would be y inverse. So the inverse of this original function is this logarithm down here. And so since logs and exponential functions are inverses of each other, all the things that we use for exponential graphs, we will also use for log graphs. We're just going to trade them. So all the x's and y's are going to trade, basically. So if you guys remember, you do not have to write this part down. But for an exponential graph, the important pieces of information were that you had the point 0, 1, because if you plugged in 0 to the exponent, you'd always get 1. Anything to the 0 is 1. You always had 1b, because if you plugged 1 in for the exponent, you'd always get whatever the base was. And we always had a horizontal asymptote at y equals 0. So when we do the important information for logarithms, and you guys can go ahead and write this part on your notes because there's some blanks there, all we do is we trade each thing. So instead of 0, 1, we're going to plug in 1, 0. So this one, the x and the y have flipped. Instead of plugging in 1 and getting b, we're going to plug in b and get 1. So again, the x's and the y's have flipped. And instead of having a horizontal asymptote at y equals 0, we're going to have a vertical asymptote at x equals 0. So when you look at the important information for logs, it's almost identical to what it was with exponents, just that the x and the y's have traded this time. So now if we wanted to graph just for a sample parent graph y equals log base 2 of x, I know the first point that I'm going to be graphing is 1, 0. The second point I'm going to be graphing is the base, comma 1, and the base here is 2, so that's 2, comma 1. And I know I'm going to have a vertical asymptote at x equals 0. So I can go ahead and here's my vertical asymptote at x equals 0. And then I have the point 1, 0. And I have the point 2, 1. And then I have my log graph. So you'll notice they look very similar to exponential graphs. They've just been reflected over the line y equals x. Next, in your notes, it asks, how do I transform logarithmic functions? So we're going to go ahead and write out the equation with all the transformations in it. And the transformations are just like normal, so this number tells you if you have a stretch or a compression. It tells you also if you have a flip. So if you guys remember, flip is only for negative numbers. Stretch is when a is greater than 1, and so that could be positive or negative. It could be 2, it could be negative 2, 5, negative 5, etc. So I'm going to say a is greater than 1. And then it's a compression if a is between 0 and 1. And that could be positive or negative. So that could be positive 2/3, negative 1/2. Any of those would be a compression. The b right here is actually a base. So this is not a transformation. That's just the base. We don't have to worry about anything else with that. Inside the parentheses tells us left or right. Positive for left, negative for right. The number on the end tells us up, down. Positive for up, negative for down. So the transformations should be similar. You should remember those from what we've done in the past. All right, next on your notes it says, how do I graph them? And this is going to feel very similar to when we did the exponential graphs. So to start, we use our 3 important pieces of information. So I'm going to have 1, 0. Then I have the base, comma 1, and the base here is 2. So I'm going to use 2, comma 1. And then my vertical asymptote this time of x equals 0. So the first thing that I have happening is I have a negative in the front, and so that's a flip. So in this first little section, we're going to do the flip part. And the flip changes the y coordinate because it flips up and down. That's a y change. And so I'm going to change my y coordinate on these. So 1, 0 is going to stay the same because if you flip 0, it's still 0. But 2, positive 1 is going to become 2, negative 1. The vertical asymptote, flipping it would not make any difference. So we're going to keep that the same. Next, I have x plus 2 in parentheses. That means that I have moved left 2. Remember, left is going to affect my x coordinate, and if I'm moving left 2, I'm going to minus 2 from the x coordinate. So 1, 0 is going to become negative 1, 0. 2, negative 1 is going to become 0, negative 1. And if I have a vertical asymptote, when I move that left and right, it's actually going to affect the vertical asymptote. So I'm going to write my vertical asymptote is now x equals negative 2. And you can think of that, I know you can't see in the video, but if you hold your arm straight up and down and then the graph moves left and right, your arm would move left and right with it. So that's how you know that the vertical asymptote gets changed for a left and right movement. Okay, and then we have one last transformation here. We have the 3 here, so that's down 3 for this column. So down 3 is going to affect your y coordinate, and it's going to be subtracting numbers. So I'm going to have negative 1, negative 3, and 0, negative 4. And x equals negative 2 is going to stay the same. So when you look at your chart, the only thing that's going to help you graph it is this final column. So we're going to graph that vertical asymptote at negative 2, and then we're going to graph those points. So negative 2, vertical asymptote like so. And your 2 points were negative 1, negative 3, and 0, negative 4. And then you can go ahead and draw your graph in. All right, the next question here is domain and range. And if you guys recall from the exponential graphs, the domain was always negative infinity to positive infinity, and then the range was affected by the horizontal asymptote. It was always a number. And so this time that's going to trade. So if we look at this, the domain, if we look how far left the graph goes, the very furthest it could go is negative 2. It just gets closer and closer and closer to negative 2 right there. But the very furthest to the right that it would go is an arrow, and so that's going to be infinity. So for my domain, I'm going to say from negative 2 to infinity. Both of these get parentheses, the negative 2 specifically, because you don't actually equal negative 2, you're just really close to it. Next, for the range, if we look down to up, for down we have an arrow, for up we have an arrow, and so the range here is going to be negative infinity to positive infinity. So if you look at these, it looks very similar to the exponential graphs. The two answers are basically just flipped, which would make sense because we basically traded our x's and our y's. All right, next it asks about increasing and decreasing intervals. So if we look at this, if I follow my finger along this, this is definitely a decreasing picture. And so when I look at increasing, I'm going to say none. But when I look at decreasing, I'll see that it decreases from
I got this part wrong on the video, so if you look at this, the dotted line is at negative 2, so the decreasing at the very left side of the graph would be negative 2, and then all the way to the very right would be positive infinity. So don't write this negative infinity, I'm wrong. For decreasing, write negative 2 to positive infinity. And I'm going to go ahead and zoom past where I messed up, which is... There I go, so I fixed it right there. That's what you should be writing as your answer for decreasing.
Okay, and then we also want to find the intercepts, and we're going to do this by graphing it. And these are actually interesting to graph, and if you have an old calculator, your calculator will not do it. So you have to use the yellow school calculators on this one. So on the school calculator, when you hit the math button, you're going to scroll all the way down until you see the letter A, and then it says log base. If you guys remember, the log button on your calculator has an automatic base of 10, and the log that we were graphing has a base of 2. So we're going to have to graph it this way. And if you use the new school calculators, they have this option. If you're using an older calculator, it does not. So you have to use a school calculator on these. So you'd hit that button first. And then we'd go ahead and plug it into the y equals so that we could actually graph it. And when you graph it, you do what you normally do. So you're going to do second trace option number 2 for finding the 0 of the graph and do your left bound and your right bound and all of that. And so here is our x-intercept, and you can go ahead and write that down on your notes. We have negative 1.875, 0. And then you can get the y-intercept by plugging in the value of 0. So option number 1, plugging in 0. And when you do that, you get that the y value is negative 4. So there we have our x and our y intercepts. And then the last question is, how do I find the local max and min? The answer is there aren't any. There's no hills or valleys.